In high-frequency trading and algorithmic market making, profitability is dictated by the microsecond. Messaging infrastructure is the core competitive advantage, where one extra context switch lets a competitor update their quote before your order reaches the engine. Most HFT firms rely on Aeron, establishing a standard inter-process communication round-trip latency floor of roughly 250 nanoseconds. This table compares those standard metrics against ZigBolt, a messaging system built in pure Zig. The results show a one-way IPC latency of 30 nanoseconds, an SPSC latency of 20 nanoseconds, and an encoding time of 0 nanoseconds. These results are based on 10 million iterations executed on Apple Silicon, representing physically validated benchmarks rather than theoretical limits. Standard code optimization hits a structural wall at the 250 nanosecond mark. Moving past it requires bypassing legacy runtimes and managing data at the hardware level. The primary barrier to deterministic, sub-microsecond performance in existing systems is the Java virtual machine. Even with garbage collection disabled and data stored off heap, the JVM still periodically halts all active threads for Safepoints. The runtime requires these pauses for de-optimization, biased locking, and stack walking. While your P50 latency might stay at 200 nanoseconds, a Safepoint can suddenly spike the P99.9 tail latency to 50 microseconds without warning. Beyond the runtime, legacy architectures use a standalone media driver daemon to route messages between publishers and subscribers. This flowchart traces a data packet through both systems. The traditional path on the left requires an extra hop through an isolated daemon, moving data across shared memory boundaries twice before reaching the socket. This routing structure injects additional nanoseconds and increases the risk of cache misses at every intermediate node in the legacy path. To guarantee sub-microsecond determinism, the architecture must eliminate both the intermediate media driver hop and the JVM. ZigBolt's transport layer is built on a lock-free single-producer, single-consumer ring buffer. In this model, the writer only moves the head pointer, and the reader only moves the tail pointer. Because each pointer is updated by only one core, the system avoids the need for heavy atomic compare and swap locks. However, lock-free atomics do not guarantee speed by themselves. Performance is often throttled by how the CPU physically manages memory blocks. This schematic shows a 64-byte L1 cache line. If the head and tail variables are stored in the same block, CPU Core 1 and Core 2 will compete for access to the same physical cache line. When Core 1 writes to the head pointer, the hardware invalidates the entire cache line for Core 2 to maintain coherence. This is false sharing. Core 2 is then forced to retrieve the data from slower main memory, incurring a latency penalty for a variable that Core 1 never even touched. Software architecture fails if it ignores mechanical sympathy, the way code interacts with the physical properties of the hardware. True lock-free performance requires the physical isolation of these pointers within the memory hierarchy. The standard solution pads data structures to 64 bytes, so each variable occupies its own L1 cache line. ZigBolt rejects this standard. It uses a 128-byte alignment instead. Aggressive hardware prefetchers in Apple Silicon and modern ARM processors do not just pull a single cache line, they frequently pull memory in pairs. This memory layout shows a head variable separated from the tail by a 128-byte gap. This distance prevents the prefetcher from pulling both variables into the same cache pair, ensuring they remain isolated. This buffer is memory mapped into shared memory, allowing two distinct processes to communicate directly without a single system call on the hot path. This precise hardware-aware geometry is why ZigBolt can guarantee a 30 nanosecond IPC latency. Once the transport layer is optimized, the focus shifts to the message payload. This is where we see the mechanics behind 0 nanosecond encoding. Working with financial protocols like FIX usually requires external code generators in Java or C++. Parsing separate XML schemas and running generated serialization code adds friction to the build process and overhead to the runtime. Zig uses a different approach called comp-time metaprogramming. Comp-time allows a compiler to execute logic and validate data structures entirely during the build phase. This moves the structural validation out of the latency-sensitive path and into the compilation step. By mathematically proving data layouts before the program runs, the runtime cost of processing that data can be eliminated. ZigBolt applies strict constraints to message structures, such as a tick message, using its wire codec. The codec requires a packed struct. This forbids the compiler from inserting hidden padding, creating a perfectly packed structure aligned to 8-byte boundaries for SIMD instructions. The compiler simultaneously verifies that every field in the message is a strictly primitive type. Because the memory layout is guaranteed at compile time, the actual encoding process changes. The encoding function compiles down into a single, aggressively inlined memory copy instruction. Decoding is similarly streamlined, operating as a zero-copy direct pointer cast against the raw buffer. 0-nanosecond encoding means the operation finishes in a handful of CPU cycles, faster than the threshold of measurable background noise. Zero-cost abstraction is achieved by mathematically eliminating the need for runtime code to exist in the first place. HFT environments are rarely built in a single language. They are heterogeneous systems. ZigBolt compiles to a standalone C-ABI shared library that is only about 100 kilobytes. This is a massive reduction compared to the 20 megabyte overhead and slow startup of a JVM-based solution. This topology shows how the architecture integrates. Using foreign function interface bindings, different languages access the same shared memory. A publisher in Zig writes data that a Rust trading strategy and a Python monitoring process read simultaneously from the same memory-mapped region. High-level algorithmic logic in Python or TypeScript can now utilize bare-metal nanosecond-scale transport. Achieving 20-nanosecond messaging demonstrates that legacy abstractions have become the primary bottleneck in modern trading. The next step is to push the physical limits of network transport even further. This involves deep integration with kernel bypass technologies like IO-Uring, DPDK, and AF-XDP to minimize the path to the network interface. The principles behind ZigBolt, strict memory geometry, hardware isolation, and compile time validation are the foundations of mechanical sympathy. The 250-nanosecond latency floor is a structural limit of the JVM. ZigBolt shows that sub-30-nanosecond performance requires removing the runtime layer entirely to allow direct hardware-aware execution.